All right, it's 1 o'clock, so I think we can go ahead and get started, at least with the intros. So today we're really excited to have Felix Santiago Collazo. He is an assistant professor in civil and environmental engineering at the School of Environmental, Civil, Agriculture, and Mechanical Engineering at the University of Georgia, which is a lot of engineering.
You're gonna change that soon.
Yeah. So Felix, he holds an MS and DS in civil engineering from the University of Puerto Rico at Mayagüez, and a PhD in civil engineering from Louisiana State University. And we have some people who are also from LSU. Felix has a professional engineer PE license from the Puerto Rico and Georgia boards and has more than 10 years of experience in flood modeling. Felix's research interests include multi-flood hazard assessment, hybrid infrastructure solutions, water equity, and flood resilience. He's affiliated faculty of the Institute for Resilient Infrastructure Systems and the Center for Integrative Conservation Research, a core faculty at the Latin America and Caribbean Studies Institute, and an engineering advisor on the board of the River Basin Center. That's a lot. Very busy. Currently, he serves as the environmental engineering subject editor for the American Journal of Undergraduate Research. So we're really excited to have Felix here today, and I'll let you take it away.
Thank you. Thank you to Erin and Aubrey for being my co-hosts over the past, 2 months or so. I was part of the faculty fellowship program. You didn't saw me here because I was in lovely Puerto Rico, part of my work with raíces, right? So that's why my topic today, or my focus today, is mostly about the Caribbean, right, and flood hazards, right? You may say, "What an engineer is talking here?" Well, I do a lot of more things beyond just your traditional engineer, right? So we focus a lot on flood modeling, and I'm just going to show you a little bit of what we do in our lab, but also, some of the examples that we have done in the past and what we're working now as part of this NCAR relationship that we're working now on. So our team, right, my team is, in short, CITRA, right, Compound Initiation Team for Resilient Applications. And the most important part here, right, me as an engineer, is to make this an application, right? I know we probably am surrounded a lot of scientists, right? But as an engineer and a person that likes science, right, I need to give it a practical purpose, right? And that's what we're trying to do. Taking those complex problems, solving it in a way that we can solve directly the society, right? I tend to ask my students, my engineering students, right, what is the difference between an engineer and a scientist, right? And they always start thinking about classes and this and that, like now, right? Main difference that we do the same thing. The only thing that differentiates is that we serve the community, right? We have to make this applicable to help them directly, right? And not just keep it at the publication level, which as an academic, I have to, right, obviously. But it's also, we need to be cautious and work for our community as a civil engineer. So that's why our group is, is this nexus between research and application. We're trying to find this best fit, right, that goes in between of them. As Erin mentioned, right, we focus on 4 main cores. We're currently doing probably 3 main areas, which is flood assessments, infrastructure solutions, but also particle tracking, right? Contamination, transport, sediment transport, right? And complex system. That has been one of our newest and more strong fields that we're doing right now. We do a lot of research, right? We do field work and data collection. We do engineering design, so you see with the students here, right? And my group itself does a lot of outreach and education, right? We believe in the strengths, how important it is to communicate, right? It's not just doing science or engineering for fun. It's also important to communicate to the people that doesn't know, right? And that's part of the things that we like to do. Some really different art projects are gonna wall your head. I'm gonna show them now here so you see what are the different things that we do, right? We're working with how we can model mangroves, right? Coastal mangroves, to use them to mitigate flooding, right? We do know already how good they are for mitigating and reducing the impacts of waves and all that, but how good they are structurally speaking, right? How putting a set of mangroves, right, can help me reduce my concrete seawall behind of it. How I can make that concrete seawall thinner, smaller, more efficient. For that, we need to know the structural integrity of the mangrove, right? So we're working that with some finite element modeling, as you see there, right? And we're modeling a lot of mangroves, right? And it's really CFD heavily, which I don't like, but the student like it, so he's doing it, right? I don't do anything, right? So we have that. We also have a work that I think was presented as part of the faculty fellowship program that we built, talking about compound flooding forecasting in the San Jones River, right? This big, huge river in Florida that has 3 big inline lakes, right? And what is challenging about them, you see the lakes there on the hash, light blue. Those lakes, right, really change the hydrodynamics of the system, right? It makes, it allows the fetch of the wind to propagate the water upstream and downstream, and can just completely change the forecast, right? And funny enough, right, the entities in charge of forecasting this, right, which is the Southeast River Forecast Center, they only do hydraulic modeling, purely downstream as it was a river, right? So then cities like when we have here on the bottom there, like there's one here on the bottom. Let's see if I can. There you go. Cities like this one here, like Astor, they just miss the forecast because they say the water's going down, but then the wind comes up, push it, and the model is not capable to obviously handle that. So we're trying to help and bridge that gap there and trying to find some science there. We're also working with structures, right? We're trying to do some marsh terracing, right? Marsh terracing is where we put this type of B-shapes, piles of rock in coastal Louisiana. And what we do that is to reduce the fetch of the wind, so then we can have better and more significant buildup of sediments, right? So we can keep our marsh alive, right? Marsh is really important ecosystem in the coast because it tends to mitigate and significantly reduce coastal flooding, right? But in Louisiana, it's a different ballpark, in the sense of how much we're losing. And lastly, we also do sediment transport, right? So we have a good project working on in the Savannah River National Lab, in which we have there hundreds, to not say thousands, of legacy contaminants like uranium, cesium, you name it, right? They're all stored within the river, within the floodplain, within its banks. And when we have a stream water event, they don't know where that sediment rich with contaminants will move, right? If it's going to go out of the site, right? What happens if it goes out of the site? It will get to the Savannah River. If it gets to the Savannah River, it's going to end up in the ocean, right? So there's a lot of things that we are trying to keep in play here, right? So that's why we're somewhat quite busy, but I'm not going to bore you more with non-interesting project. Well, let's talk about floods, right? That's why we came here, right? So we have a lot of natural hazards, right? However, if we go back into the history, right, the most significant are from water-related hazards, right? Those are the ones that bring more billion-dollar disasters at the U.S. I need to probably update that chart with the new ones, but also at global disaster, right? And it probably is not a mystery, right? Because again, when we have these big hurricanes, right, their effects can be felt impact so far inland, right? And in different ways, in different fashions, right? So our group has focused a lot on flood hazards because again, I come from Puerto Rico, right? An island that is, full of water around, and we don't even know how to manage it, and we're so prone and all that. So it's kind of obvious for me to try to bridge that gap in terms of flood hazards. But what could be, from those flood hazards, what is the most deadliest, right? So from those, we have the lovely storm surge, right? Storm surge is when we have the wind blowing perpendicularly to the shoreline, right? And as you see in this graphic, as the winds keeps pushing that water, right, the water will start rising, right? And this is a simple momentum equation continuity, right, type of scenario. If you have more water moving faster, right, what's going to happen, right? Remember your Q equals B times A, right? It has to hold, right? So then the water has to rise. So therefore, this is where, specifically in the Gulf of Mexico, right, you have those significant surges, right? You need really flat bathymetry, really extended in terms of distance, right, to build that fetch and to rise that water, as we see in those type of drastic scenarios. Do we see that worldwide? No, right? It depends a lot on the bathymetry, on the topography, the coastal geometry, and so on. There are many factors that involve what will be your surge flood hazard. On the other side, right, inland, right, which you probably will feel here more in Colorado, right, we have river floodplain, right, and inundation, right? And this is quite fun because, again, you start to think how people understand, right? If you have the money, where are you going to live? Probably near the water, right? Why? Because you like seeing water, right? Water has this calming feature to the human, right, that makes you feel relaxed. Let's be honest, right? You go to the beach, you're not going to get the farthest hotel from the beach, right? Probably, if you have the money, you will book, beachfront and all that, right? Because again, it's something that we like to see. But then when we don't plan it well, then comes the disasters that we see, right? If you're too close in the floodplain, right, your rainfall will start increasing those river flows. When you hit that bank, it will start getting out into the floodplain, and you have the disaster that we have, right? And that's our fine. Again, all this has always existed, right? And we have to, study this for decades. But the question is, what happens when we have both, right? And this is where we come into the word compound flood hazard and multi-flood hazard, right? And again, this is nothing new, but we probably have been in silos, right? We have our coastal engineer doing our stuff, we have our hydrology doing our stuff, and we don't care because you're here, I'm there. But at the end of the day, in the estuary, right, this is gonna happen, right? And in islands specifically, right, all the islands, most of them, all the rivers drains into the ocean, right? And we don't have that capacity of reservoirs and things like that. So then they're gonna be prone, right, to what we call compound flood, right? Which is when we have this combination of both, right? Hydrology and coastal processes, right? And it can be through the coastal floodplain, as you see in the bottom, where you see the red arrows of the search going into the coastal floodplain and then mixing with the rainfall runoff, or it could be through the river, right? In which the stream flow gets battling with the storm surge to see how far it goes inland or how far it penetrates, right, and all that. And this is a really complex problem, right? It's not because we probably are scared to deal with it, but it's really mathematically complex to solve for, right? And that's why we have deal and try to do really different approaches, right, in terms of coupling different models, different data sets. But again, at the end of the day, I don't want to say here which or which approach is better than the other one, right? At the end is what you have in your hands, right? As I said to everyone, I prefer you consider the compound hazard in your models and when you're in the estuary than to just completely ignore it, right? So therefore, it's something that we need, this probably field started strongly, I want to say probably around mid-2010s, right? Which we start more people investigating and doing more of this. But again, this has been always here, right? And that's where we start to move now, right? So, when we have this compound flood, right, it's mainly when you have what? Two events happening, right? Probably like a low pressure system with a previous rainfall event or a hurricane with this and so on, right? When you have those co-occurrence happens, but more than likely also, or probably more often happens when you have a hurricane, right? A tropical cyclone is probably the best example to bring you this compound flood. And you may say, well, and again, this is probably bullying FEMA, right? The entity that protects us supposedly, right, from flood regulations and so on, right? They want to say that, oh, well, compound flood doesn't happen, right? Specifically in the U.S. mainland, right? Because we got big watersheds, right? And our watersheds are low gradient, right? Most of them, right? And they're going to take a lot of time to drain that rainfall that fell to then meet with this coastal storm surge at the outlet of the river. True, right? In most cases. But in islands, right, in which you have a steep watershed, and it's really small, that's completely violated, right? And, still we use the same tool, right, those FEMA maps for somewhat forecasting or trying to plan ahead, right, what will be the disaster. So therefore, that's not true, right, in the islands, right? But also even in some cases, right, in the mainland could be violated, right, depending on the conditions, right? So hurricanes in the Caribbean, right? Again, the talk is about the Caribbean. I'm going to show you some examples of the Caribbean. But in the Caribbean, I'm from Puerto Rico, right? A small island that is probably you don't see it there under that big cloud, right? But before all of this, right, we had Hurricane Georges in 1998, right? It went through the east, went through the west. I probably was like 6 years or so. I remember going out and seeing the eye. Like, it was so calm. Now that I'm, older and I try to track it back, I see like, oh, look, the eye passed probably through my home. And it was true, right? And my point is this, that hurricanes tend to impact a generation, right? After my, 6 years, you don't probably remember nothing, right? After that, no more hurricanes. No, like big impacts, like none. Like we were so lucky, right? And probably the majority of folks will laugh, like the hurricane is coming, and then the day before, whoop, veer north, veer west, nothing happened. The government canceled classes, everything, and people were mad because it was just a sunshine day, right? Which is good, right? But then came a couple of them, right? So we have here Hurricane Irma, right? Again, nothing from 1998, only some few tropical storms really far away, right? Then comes Hurricane Irma, completely devastated San Thomas, right, and San Croix, and St. John, right? But also the northeast east part of the island, right? So again, it was a category 5, right? That went through, didn't even touch Puerto Rico, but had the wind span was so big that completely devastated a lot of the homes on that northeast tip. Then what happened 2 weeks after? Well, we have lovely Hurricane Maria, right? Who just came and changed history for our Puerto Ricans, right? It completely wiped away the island, in my opinion. You see the lovely eye there. That, you know, when the eye was passing the Lesser Antilles, as you saw there, my dad was one of the ones that's not gonna come. That's gonna always go out. And I'm like, I don't think so. And then you will see the news meteorologists crying live, like this is really coming, right? And a lot of ignorance, right? And a lot of this, how we call this, not knowing because we don't communicate well, got a lot of lives, right? And I'm gonna show a little bit more about Hurricane Maria. But after that, what happened 5 years after that? We have also Hurricane Fiona, right? And the fun part about, well, fun and not fun, right? The interesting part about this is that Maria was a category 5 and people got really disaster, right? And they got the issue. Then comes Fiona as a category 1. And people are like, no, I got survive here at category 5. I'm gonna be fine. No, my friend, it done more rain than Maria, actually Fiona. Why? Because it was a low moving system. I think it was, if I recall it well, between 2 to 5 miles per hour in those last stretch. So he stayed a lot there in that southwest part south. And people just thought they were not getting flooded and they just stayed there, right? And they got really well, right? Worst conditions. So and then let me show you a little bit about Maria because again, I like to show this to people, right? So this is Maria when it passed through, right? Again, I live here on the southwest, right? Again, I was there during this event. And this is one of the biggest rivers that we have that drains a lot of the southwest. You see that overwhelmed, you know, what's within its banks, nothing major, that's good. Again, where I was, we so much experience a Cat 1 type of impacts. Obviously, northeast of that red line, it was like Cat 5 or so, right? And then you see, you know, other places that I went to so afterwards, right, which is still on the good part. You see some erosion, right, from the rivers and all that. Houses that are probably gonna not be more livable. On the west coast itself, we got a lot of destruction from the storm surge, right, which is quite interesting, right? Homes completely on the water. And then, you know, you have closer you get to the line, right, you see a lot of the roofs, like there's no roofs, right? There's no homes, right, period. There's even videos of concrete slat roof just pulling over, right? That tells you how much was those wind speeds, right? And then we have this really interesting community, right, which got isolated after the event because they only have one bridge in, one to get in and out. They have to throw a cord, and that's how they go to groceries and all that, because if not, they will not even able to make it, right? So just some numbers, right, for you to feel good or bad, right? Or do you probably a bit more of importance while you're doing this job, right? Again, 100% of the power when we went pitch black, right, for a couple of days. My home, we were 20 something days without electricity, and again, we were Cat 1, right, type of scenario. I do know people were 9 months, 12 months, probably more without power, right? A lot of the places, right, are uphill. They need pumps to get the potable water up. So we got 20% of loss of the potable water service, right? I was lucky enough to have water. More than 250,000 of homes were destroyed. That's not fun, right? And again, 49 bridges, $2 billion of agricultural loss, right? And so on, right? Again, there are more than 2,000 deaths, right? Officially, there were 64, but again, we don't even trust that number well, right? And again, 90 billions. I think it's one of the, it's on the top 5 most disaster of the U.S. Obviously, the most for Puerto Rico, right? Some examples, right? This is from Coastal Search, right? In terms of disasters. It's kind of fun because then you see here, let me see if I can get, there you go. Kind of like see here, the whole pool went to the ocean, right? It's kind of fun, right? Like you're in front of the ocean, what do you need a pool, right? So now the pool go back to the ocean. But all that on their foundation of that building got completely washed away, right? And that same building that you see in here, right, is this one here. It's kind of like completely tipping front, right? I went there to make like a video recording because I went like 6 months after it as part of my LSU work, and you see the doors opens of those apartments. They left everything. They cannot take anything. They have to evacuate immediately, and they're still up to there like that. Like all of that is full of people's stuff. No one can get there because at any moment that can just tip, and it would be a major catastrophe, right? From the riverine perspective, right, for hydrologists here, you kind of see here, let's see, this is before of the storm. You kind of like see here the path of the river, right? And this is afterwards. You see that we got a lot of new bogs, lakes, cuts, right? Completely changed the geomorphology of the area, right, of that river. And, you know, this one completely wiped away bridges. You see the water, again, it's completely, this is the bridge, one of the bridges, right? Should be right around here, completely got wiped away, right? So again, impacts of hurricanes are significant, right? And it's just how we try to build something that is more resilient, right? So that's why kind of like the motivation, right, that we have for my team and probably our work, right, is how we can take the things that we know that works at the US mainland, for example, right, that's the analogy, all those great things that we do, and apply it in places that we really need the effort, right, that we're really vulnerable there, right, and not just another pop, right. Again, we don't have a lack of numerical models. It's probably we have a lack of funding, right? That's mainly always the issue, right? So therefore, we need to start to do stuff that are more driven by this and not just by the funding. And again, not all the complex problem needs complex solutions, right? And that's what we're trying to do. You know, it's always better to have something than nothing, right? As long as you obviously tell us what it is, right? So for that, we're gonna show you 3 examples here, right? So first of all, we have, we're gonna talk about Havana and Cuba, right? We have a Puerto Rico project that is probably somewhat completed. And then we have what we're doing for the rest of the Caribbean as part of this work with NCAR, which is somewhat starting, right? Okay, so I have here, let's see, let me go. Oh, okay, so I will show you as we go. So this work, you may say, well, yeah, we work with Cuba. Don't ask me how, right? Quite difficult to work with Cuba with the experts control that we have nowadays. Surprisingly enough, back in the previous administration, right, 2017, my LSU advisor went with a delegation of probably 40 people from the Louisiana state and went to Cuba. Like Department of Agriculture, you name it. Like, it was a different time, right? That's where we got this great connection with them. And Cuba has a lot of interesting problems, right? We're gonna show a little bit about them, but this is what you're seeing here is the what they call El Malecon seawall, right? It's one of the most picturesque waterfronts that they have, right? It's preserved by UNESCO and all that. But Cuba is like a bowl, right? Specifically this part. Once the water overtops, right, from that surge, the seawall overwhelms through the sewer drainage, right, that obviously discharge to the ocean, then all the water stays there, right, because it's a bowl, right, and they have a lot of flooding that stays there for days, right, and so on. So a couple of things that we're trying to do is to help them provide a better, again, they don't have any coastal flooding forecasting, obviously, or anything close to that. And then what we're trying to do is use this simple approach of reworking our coastal model that we use, which is ADCIRC, advanced circulation, with a third wave generation model, SWAN, right, to try to provide a better storm surge styles and ways, not forecast, but assessment, right? We're not on the level of forecasting, not even close. We did simulate some hurricanes, right? But the point is here that we're trying to increase is that resolution around the island, right? That's the most important part. For any flood modeling work that you want to do, you want to be high accuracy, right? High resolution in areas that you are of interest, right? So what we're trying to do is to grab this big mesh, which is simple, right? And just carve out Cuba, improve that accuracy around it, so then we can provide better simulations for that coastal flooding, right? And with that, I have an example here that I want to show you, which is Hurricane Mitchell, Category 4 at landfall in Cuba, right? And Cuba is quite interesting in the sense of how the flood dynamics works, right? You see here, you will see here that on this gulf, right, surge is the predominant factor because it's really shallow, right? Whereas on the north part of the island around here, right, which is where you have the Havana, wave is the dominant factor, right? Because it's a big trench that you have there, right? So then Cuba needs this type, and the same happens with Puerto Rico, right, in the north and the south. So Cuba needs to kind of identify, right, what are the main sources of issues, right, and how we can deal with it, right? So that's somewhat what we have done with Cuba. What we're trying to do in the near towards long future, right, because things have stalled out with the current administration, right, obviously, is that we want to improve the resolution, right? We want to go from 100 meter to 30 meters so we can capture that seawall perfectly, right? They surprisingly enough, right? they do have a 20 centimeter resolution topography, right? You might think, well, that's a third world country. They don't have anything. No, it's all the same. That's a whole lot for the whole, Havana area, right? And a fun fact that I like to always highlight, you see this place that is completely flat? What that could be? The US Embassy, right? Because they cannot overflow there, right? So funny enough, they do have some really good quality data, right? Like they have map out all the stormwater infrastructure, right? Location, pipe, diameter, slope, everything. Me working in Georgia, I can tell you probably a handful of cities that have this. Again, rural Georgia is just a mystery where you have your stormwater pipes. So we do have this, right? So we're trying to just work it out so then we can have this combination of rainfall, storm surge tides, waves, and also the stormwater infrastructure system, right? So then we can kind of see better the behavior and the patterns of that flooding. So moving towards more, how we call this, not real work, but done work, right? Probably finalized work. Let's put it like that, finally, right? In Puerto Rico, we have done a couple of things. We did Hurricane Georges, which I'm going to show you a little bit more. And this is, again, I probably talk about it, right? Hurricane Georges in 1998. It was so fun from a hydrometeorological perspective because we don't have one. We only have stage 1 data of the radar, right? This is 1998. There's no rainfall. There's no QPF. There's nothing. It's just reflectivity, right? So we have to do a lot of magiciancy, right? And a lot of black wizard sorcery to transfer this into rainfall and then somewhat calibrated and verified and so on to get some rainfall inputs, right, for a model. But again, this work was done probably mid-2010, so there was no more hurricanes. So then what flooding I can assess, right? So we have to go back to 1998. But Georgia is where I went east to west. It produced like a 10-feet surge, 10 inches in 2 days, right? And affected a couple of significant places, right? And we just focused on the East Coast, a couple of watersheds, right? We already had, and we still have, a good working coastal flood model, right? And that coastal flood model, as you see here, right, that's like the whole stance, right? It has probably, I want to say, 1.8 million nodes and easily 1.6 million nodes is only around the island of Puerto Rico, right, and the Virgin Islands. So it's really packed dense. We go down to the 30, 50, 60 meter resolution throughout the shoreline. So it's really good. And you kind of like see here how you can see like the maximum elevation surge, right, for those, for that hurricane, right, on the East Coast. And what we did, right, again, we are trying to do compound flood, right, rainfall and coastal flooding into a single. So what we did is that we took the coastal flood results, extract those results, right, in a sense of a time series water surface elevations, right, on those red points that you saw there, right, and include that in my hydrologic model, right. This is what we call a one-way coupling, in which we pass information from one model to the other one, right, and then we let it just run and let it combine itself there, right. In that sense, all of those dots have a water surface elevation from the coastal surge, right. And once you put it there in the hydrologic model, then you're gonna let them move and let them combine, right? And that's what we kind of did here. Did I probably overshoot it? Yes, I want to say yes, because again, that's a 30 meter resolution mesh because my hydrologic model was a 30 meter resolution mesh. My sturgeon change each 30 meters, not that much. So you probably can refine this to make it more where you see really differences, right? From your coastal flood perspective, so then you have this high computer intensive coupling, right? So let me show you an animation here. This is the Demajagua. So let me go back here quickly. This is this pink watershed that you see over there, right? We're focusing on that outlet portion of it, which is this, right? And drains into a really attractive marina for boats, as you see there. I'm gonna hit start now. And that first flooding that you saw were some outer rain bands from Hurricane George itself, which tends not to be traditionally, right? That's another rain band, right? That produce, again, this is small, really small. Again, we talk about 4 square miles, right? It's really small. And then you start seeing there, right? And then what you see now will be the penetration of the storm surge, right? And there you go. So it's kind of interesting to see that in this specifically event, we did have first the rainfall runoff flooding and then come the storm surge, right? Recall what FEMA says, right? FEMA says the opposite. First comes the storm surge, and while the storm surge happens, all the rainfall falls on the upper watershed, then it takes a time to drain. Again, the dynamics of a small, steep watershed, right? And specifically the outer bands, right? Which is tend to be not well captured in synthetic modelings, right? Which is what we tend to do for those forecasted, for those assessment models, right? And if we just frame this into the maximum, right? On the left, you have max flood depth only with the rainfall runoff, right? You have with the combined. If you're a hydrologist and you're gonna do probably again on the old time, right? You will do the left one, right? You're missing a lot of the flood extent and the flood depth, right? So that's why, again, the message with all this is that I don't care how you combine it, but you need to combine it, right? You need to account for that, right? In some fashion way. Now, what we're doing now, or what we probably just finished now, is we're doing more region-wide flood mapping approaches, right? And again, that small watershed or those 4 small watersheds took a lot of time and effort, right? But again, you may not have that same quality, right, for all the places, right? So we're trying to use this approach of let's try to make this coarser but still accurate and representative to the conditions, but you can go bigger, right, in terms of area and expand, right? So that's why we went with this 2D, 1D approach to then do 85 watersheds, right, on the southeast, and east part of the Puerto Rico, right? We're talking about 22% of the total area of the island, right? Obviously, we excluded any watershed that had reservoirs, right? And most of them drain towards the north, so it's not even a challenge here. So all of those watersheds are all coastal watersheds, right? Then we combine this with synthetic storms, right? And rainfall from them. And then we were able then to make freshwater flood maps. And then we were later going to show you how we combine it with saltwater flush map, right? To have this compound flood situation. So just looking a little bit more into this 1D, 2D approach, right? Again, I'm just zooming into one of them, right? What we focused was on the following, right? We do know we have this type of rule of thumb in which storm surge doesn't go higher than the 10-meter elevation, right? If you think about, right, change that to feet, right? We're talking about more than 30 feet, right? Katrina, right? Hurricane Katrina was 26-ish feet of storm surge, right? And that was, again, a rocket, outlier event, right, in the Gulf of Mexico. So we know that the rule of thumb tends to be no more than 10 meters, right? So then we ended up making our 2D model, which you see there in the red hash area, up to the 10-meter elevation contour, right? Why? Because I know that at the 20-meter elevation contour, there's not going to be no surge, so there's no compound flood. So then what is the need of me self-extending and, over-computing where it's not going to be any compound flood, right? And then the rest of it, which you see in white, are, your simple 1D watershed modeling that then gets fed into the 2D model as, your typical boundary conditions in the river. So with that, again, we had already from the sponsor, I think it was 410 synthetic storm tracks, right? They were based or derived from history, right? What you see there are the 4 more common trajectories where you have a hurricane impact in Puerto Rico, right? And then they just extended the track line at certain degrees, and then they just changed the categories of the hurricane from 1 to 5. I'm a fan of that. Somewhat not, somewhat, yeah. There's some flaws, but it's what we were given, right? Like, for example, the forward speed is not being changed, right, of the storm, which makes a big difference, right, in freshwater flood mapping, right? But we take that. We then did some parametric precipitation modeling, right? We went and we estimated what was the somewhat best model for Puerto Rico. There's already some studies done on the U.S. Saudis, and we just somewhat duplicated or extended that for Puerto Rico, but also not only at the atmospheric level, but also at the hydrologic level at the watershed response. Ended up being the FRAM model, right? The best ones for now. So then with that, I can take that synthetic storm, which just have, 5 parameters, get that as synthetic rainfall event, right? And put it on my model, right? So then we can have my 1D model, which was SWMM, get a hydrograph from that, give that hydrograph at the upstream boundary condition to my 2D model, which is a GSSHA model, add also the rainfall, right? And that's how you get this type of animation of a flood map, right? So just be patient. You're going to see now, it's how you see quick flash flood event, right? And then drains into the bottom, right? And that's kind of like the maximum of it, right? With that, we're able to then, again, imagine this, right? We run 85 watersheds. Some of them have 3 or 5 tributaries, so 3 different or 5 1D models, right? 410 times, right? Because we have 410 storm, right? And post-process all that to get us what we call here, right, a freshwater flood map, right? the client or the sponsor was interested on labeling by category. And again, this is a conversation for another day, which is kind of interesting, right? Because their justification is that people understand only by hurricane categories, but we all know in this room, right, that the hurricane category is not even close to be a representative of the freshwater flood, right? But we put it, right? We also did it the other way for science, right? Which is currently under revision. But you kind of see like this is a way or framework, right, that we can try to do to then have a lot of it. Again, GSSHA, right, the hydrologic model is not paralyzed. It runs really, each of those watersheds took like 4 hours to run that event. It was a 2-day event. So imagine us, we run like, we put this on the supercomputer on series, right? But we have like 80 models running at the same time, right? For a couple of times. So it was quite interesting, but you kind of like see here, you probably will not notice it that much, but this is category 1. Look at the colors in some places. This is category 3, right? You kind of like see on this upper portion how it really changed significantly, right? And then category 5, right? You almost see a lot of change, right? In theory, what we saw was that the category 3 hurricane was the one that produced the significant flood event, right? And we were like, why the category 3, right? We never saw a monotonic increase like with the increase of the hurricane you get now, right? But the category 3 was the one that produced the highest flood depth, right? We went back and see why, right? Again, all the storms, they move at the same forward speed because there was a limitation from when they make the storm, right? We ended up finding that the category 3 hurricanes, right? And again, category from 1 to 5, right? You increase the wind speed, right? You decrease the velocity. But what changed was the size of the storm. Like category 1 to 2, you are a small storm, get it bigger. Category 3 for some reason was the biggest one. Then 4 went a little bit smaller and 5 a little bit, but the category 3 was the biggest span of that wind field, right? So therefore, more of my watershed is getting more flooded because your rainfall field is bigger, right? And that's why we saw that again, but all this was attached to that formulation of those storms, right? Now that we have the freshwater flood map, right? Our goal was to combine that with an existing storm surge flood map, right? Again, the client already had a storm surge flood map for the whole island for categories, and they want to see compound flood. So I'm not gonna run, as I showed you before, right, those 30-meter points combined because I will never finish, right? Again, that's really intensive, right? So we went a way of combining it afterwards, right? That's why we use the same storms that they use for the storm surge map for the freshwater flood map, right? Because then I'm probably easier to combine them, right? Still don't combine it one plus the other one because I will cry. That's the worst thing that we can do, right? Because we know that coastal hydrologic processes, they are non-linear, right? Effects, right? So don't ever try to combine them. So this is, kind of like an example of those storms in terms of the coastal flood map, right? That they already had. But again, all of those flood maps were already provided, right? It was part of their work done in the 2015 or 14, right? So there you go. That's the storm, right? And it's gonna start flooding, and you see kind of like someone probably could make it faster. But then you see here the maximum, right? So then they just repeat this and do the maximum of maximum per category, right? So now that I have, right, I do have now what? My freshwater flood map, right, I show you, right, with some 2D, 1D modeling. The storm surge map, which was already somewhat given. Now we put it in our lovely black box of AI, right? And we get an output, right? We ended up using deep learning model. Was quite good for the watershed that we again, a lot of this is on the review now, and we can chat more offline. I think I already presented a lot of this on the previous talk that we gave. But what we ended up finding is that the combination or the deep learning does a good job combining them. Again, we put both freshwater and saltwater map, right? We have to add some other combination to it, right? We added the topography, right? The land use, land cover, infiltration now, rainfall rate, right? We added a lot of different variables, and we let him find us which one is the best combination, right? We then, again, use our compound, or obviously for this, we did it 2 watersheds. For one of the watersheds, we took it and we run the compound flood model, right? The one that takes a lot more time, right? It was a hassle, but then that was my real observed value, right? That's the value that he used to train its machine learning, right? And then we use 75 for training, 25 for validation, and we ended up noticing that it's really good, it tends to be really good for that watershed. So it was good. The problem is that you have to transfer it, right? And that's where we didn't went deep enough, obviously, and this is where we see future work on the transfer learning approach to kind of like improve this, because we just completely took the outputs, right, or the solution, and applying a next watershed. We went with a watershed which is close enough, so then they're kind of like homogeneically the same. It was a failure, right? It was really bad. And then we even went the other way, and it was probably, like we trained this one and we applied to the other one, right? The original one. It got a little bit better. But in theory, what we found is that there's a lot of more work that needs to be done in that transfer learning approach, right? Specifically for this type of combining flood maps, right? Again, it's good, but then you have to redo everything, right? All the watersheds. So then you beat the purpose, right? So that's kind of like what you see somewhat here, right? One after we combine it, right? This is category 1, category 2. You start to see the changes, right? Category 3, category 4, category 5. And again, you probably didn't saw a lot of changes in the freshwater flood maps. So most of these big changes have we moved from 3, 4, and 5 is because of the storm surge, right? The storm surge really starts dominating the flooding more than the rainfall, right? On those eastern portion, you see down the red, right? And so on. But again, that's currently under review, and I'll share with that you later more. So what we're doing now, right? That was probably past work, thankfully. We finished that chapter. Now, what we're doing now is this great work with the NFS, actually, in their shared program, right? And this work is a 5-year project in which we're trying to develop or co-develop, right? Flood mitigation solutions with the residents, right? And the goal of this project is not just say, hey, I come here to help you, give me your data, and I'm out. No. Here we're sitting with them before anything happens. We're learning from them. We're sitting on the table. We're seeing where's the flooding happening, how it's happening. We're getting that local knowledge that is so important and no one tends to use, right? And we're giving it their value and their place in the board so that we can have educated decisions, right? And we're focusing on 3 watersheds that drain into the San Juan Bay estuary, right? As you see there, right? We have Juan Amatos, Puerto Nuevo, and Martin Peña. There are 3 communities that are really completely different in terms of organization and solutions, right? But with this, we have an anthropologist helping us. We have, I don't know what else we have. We have meteorologists. We have a big group of people here that's gonna help us to untangle these issues. With this, type of project, again, we're trying to, learn how we can design as engineers solutions with the people, right? We're also gonna have 2 syllabus learning projects in which we take our students from our senior design class, and they're gonna go and design and give us solutions like a construction plan and how to solve it, right? So just not, just beyond getting them to do this, they're also seeing culture, they're seeing a different geography, they're seeing people, right? They're trying to serve the community as an engineer should do. We also have flood sensors that we're gonna be placing in the Caribbean. Well, in Puerto Rico will be the first one of this technology in the Caribbean, right? We partner with the people from FloodNet in New York City, in which they have like 300 or so of this throughout Manhattan, Brooklyn, and all that. And these flood sensors are really cheap, right? This one that you see here, and you see it over there, they go on the stop signs, right? And it's to monitor urban flooding, not river flooding, right? You can also do it, but more like to see what are those patterns of flood, so then we can see if our models are working properly or not, right? And if we can confirm what the people living there is really true or not, right? It's always good to double check that. But this one costs like $250, as you see there, everything. It transmits to LoRa, which is like Wi-Fi, so you don't need a cellular network for that. And then he can collect everything into a Wi-Fi box and then send it to the cloud, and then you can process it. So we're gonna do 30 of those, 10 per community, and the really fun part is that high school students are building it, right? We had a great experience. It was late May, and we had already 5 of them built. A lot of the students burned their fingers with the soldering, but they learned to it, right? And now they even have them as part of their science projects for their fairs, right? And it's really good because the students are really adapting, right? And that's the point. The point of this is we are trying to find students or community members from that community so they can do it, because then they will adopt it and they will defend it, right? And that's kind of like the idea that we need to move and not just come a foreigner to put a sensor there, right? And kind of like, oh no, I'm gonna steal it, broke it, I don't care, right? So it's part of the education with the community. We also doing current and future flood maps, right? We're trying to update those flood maps that I showed you from that 2015 study, right? With more diverse storm set, right? This is from the storm database from Bloomingdale, right? and you see how much variation we have on those tracks versus what the ones that they have, right? Over here you have 500 or so storms that make landfall to Puerto Rico based on historical conditions, right? And then you kind of like see here a recreation of that map from those storms for just like a maximum of maximums as an example, right? We're now working to do the same thing for future conditions, right? And see where you have those gaps, right? And lastly, we're doing impact-based forecasting, right? We're trying to place or do, probably towards the end of the project, obviously, what we call the first pilot project for impact-based forecasting, right? And what is your typical forecasting? Well, we say, oh, it's gonna rain 3 inches. Be careful, that's probably it, right? And in Puerto Rico, it's even more challenging because the rainfall forecast is so hard that they only say the whole city is under flood alert. Because if the forecast misses a couple of kilometers, it changed the watershed and completely inundated another community that they were not aware. They just prefer to paint the whole area, right? And while that is safe, it tends to be a lot of misleading communication. And when that happens, people get mad because, oh, you tell me it's flood, I'm not gonna do anything. And I had a beach day that I could not even take, right? And then people get, people start undermining the weather forecast people job, right? So the idea of this is like we're trying to build from the beginning where, how, and then impact-based forecasting will be, right? When this happens, how that affects you. So instead of just telling you, oh, you're gonna have 2 inches of rainfall, you're gonna have 2 inches of rainfall, but this street is gonna be flooded from this time to this time. Try to get an alternative route like this one, right? And I know that sounds really great, but probably really complicated. And it's something that we cannot see nationwide, right? But we need to start moving that way, right? We need to start seeing and trying to see if going to that micro level of how that affects the people could help really their daily life activities and not just, well, another flood event, right? What I do. So that's where we're trying to work now. We're doing flood mapping activities with the residents to know where are those spots and how they affect their daily activities. We're doing already community walks, learning the system and seeing how things are happening. And now lastly, but not less importantly, we're gonna talk to you a little bit of what we're doing now with NCAR, right? That we started probably throughout this summer, and obviously not gonna be done over the summer, right? It's a lot of work, but we have 2 main tasks here, right? First of all, we're trying to do a comprehensive coastal flood hazard assessment for the Caribbean. I was lucky enough to have the student that helped us during our workshops this summer. She just got a GRFP, right? And she now has freedom to do whatever she want to do. And she just took this as one of her things to do. But all the red polygons that you see there, we're going to have a coastal flood model for those islands, right? Right now, the Caribbean is, again, it's just blank. We only have Puerto Rico, the U.S. Virgin Islands, at much to say a lot, and the rest of it is based on the country. We know that making a flood forecasting model takes a lot of money, right? And resources, right? And that's not going to happen. So what we're trying to do is to see, obviously, we're not going to go forecasting, obviously, but what is their vulnerability, right? Their risk, their hazard to those coastal flood events, right? So we're going to take, and I will show you a little bit more the approach, right? But again, we're going to take, I want to say it's probably around, well, I'm going to go here to the next one, 30 islands, right? That we're going to assess, right? In which we're going to go in a process of extending the coastal flooding inland, right? So then, because right now all the flood models, they just have the island, that's it. So that they imagine like the water just stops the shoreline, which we know is not true, right? So then we want to see how that impacts, right? But no, why not 10 meter? And then I'd say I'm changing my ballot at 30 to 20 because we have some really good cliffs over here, right? A lot of these islands are so steep that if I do probably 10 meter, we just have a sliver, right, of land that will be in my coastal flood model. So then we are playing with how high we have to go so we can have enough boundary, right? But then we have to be careful, right? Because the higher we go inland, the steeper slope that we have, right? And that tends to be also problematic to any flood model, right? So we're gonna do, and this is probably what we did throughout our faculty fellowship program summer workshop that we have, in which we show a couple of you how we can build the coastal flood model, right? So here you have the shoreline, right? And then after we do the shoreline, we're gonna go inland, right? And we're gonna play with the resolution, right? Because again, we have a small island, we probably can do 50. If we have Jamaica or Dominican Republic with Haiti, we have to do probably 300, right? But then we go and we extend, right? So again, I'm making a hole on my big mesh for the whole Caribbean to extract that island, change the resolution around the shoreline, and obviously we need to start going from small to bigger, right? That's why you see the transition. And then we go inland, right? So then a ferry goes from the shoreline towards the ocean, and then we go from the shoreline towards inland, and then we combine, right? That way I can have a working mesh that then can be connected, right? As you see here, right? Again, this is still work in progress, right? Don't take a look at this ugly element, right? But then the point is to go from not having anything that goes inland to going and seeing where it's gonna be flooded and who's gonna get affected, right? And then at the end, we're just gonna take this big mesh, plug it out, and put it in there, right? With the goal of having all of those islands under the same numerical model or mesh, so then we can just run hundreds of storms, right? Instead of running them, all of them individually, right? That's probably a waste of computer resources. And again, we're gonna run a couple of, I don't want to say the number, I don't know, but we're gonna run synthetic storms, right? And then we're gonna estimate the flood frequency and impact, right? We even have that we found some of our friend Germans, they publish a worldwide building footprints. So now I know in these Caribbean islands, where are the buildings located? So that now I can do some Jesus modeling. We can do a lot of stuff now because I'm just going inland, right? So now we can see what type of buildings being flooded and how much. And then you can do estimate loss and so on. There's a lot of things that could come from this. Lastly, what we're trying to do now, actually more me, right, as part of what I'm doing here, is to try to improve the rainfall, right, in the compound flood, right? My goal is to take the advantage of this ADCIRC simulation storm, right, and put the rainfall on it directly, right? So we can let it run and mix itself, right? Tends to be a little bit problematic, right? Because when we have steep slopes, right, the water gets so shallow so fast that tends to explode, right? So those are the things that we're trying to work now. We currently have a slightly working version that now uses, instead of the rainfall, the curve number, right? Because again, ADCIRC is not a hydrologic model, right? So if I just put rainfall there, I mean, it's represented that everything is impervious, which is not true, right? So now we have a way that we pre-process everything and give you the rainfall runoff itself. So then we are moving the runoff and not the rainfall itself, right? So we can make it more realistic. And again, we are playing with something like this, right? Again, we have our turquoise here is our ADCIRC, right, domain. And then we have upstream conditions that attaches to that mesh, right? That we need to account probably in a 1D because it's too far away, then we're not gonna go inland, right? And then the other non-contributor areas is what we're trying to define now if they are really worth it to contribute in it or not. Right? Our goal is to see, is that blue area is gonna change significantly my compound flood levels downstream. Not, then we don't need it. And now instead of me just trying to map out everything and model it, I can find a way that I can determine how big is the area needed to be to contribute, or what type of properties that watershed or sub-watershed needs to have to produce a significant compound flood downstream. So therefore, I don't need to run everything because in theory, maybe not be needed, right? With this, I'll finish, right? In the sense of, right, we need to solve things in an easy way, right? This cartoon, I like it a lot because it tends to portray the issues that we have as scientists, right, and engineers. We don't know even how the world to communicate flood probabilities, right? Imagine someone that is living in the action, right? Even still, our news meteorologists, right, and the communicators, they still get confused, right? So we need to work around this, right? So when we provide solutions, people can understand it, right, and can work towards that. With that, I finish. I'll be happy to take any questions.
Great. Questions for Felix? Yeah.
Sure. Great talk. Thank you. So my question is on this, like the two types of model that you are trying to couple, like the rainfall runoff and the coastal storm surge. So do you think, and you did that with a kind of AI component. So do you think that you need a kind of physical model to, for some low gradient areas? Because this surge can have impact on the upstream as well. So do you see that you need to do this as a kind of coupled way?
Yeah, so I'm gonna say that, I'm gonna hate me if you want to, but AI is not even close to replace physics-based modeling. I'm gonna start with that. There's a lot of push for AI. We tried with AI. We didn't like AI, right, at the end of the day. So we still think that physics-based modeling is the way to go. When we talk about this complex compound flood, forecasting and hazards, I see way far the AI to get into that. And again, I know there are publications, I know there's stuff around, but it's just a matter of even the physics, right? That are not probably even well portrayed here, right? So towards your question, right? What we tried to do was mostly combining outputs instead of, the modeling itself. So that could be differently, right? Because you have an output versus trying to replace a model with AI, right? That's where I don't think we're close to it in terms of AI. Hopefully we don't get there because again, I'm probably another way. I prefer my physics-based modeling than the AI. But it's kind of scary because everyone is putting their eggs on that basket of AI for everything nowadays, right? If you kind of see like, the AI has improved the hurricane forecast, right? From the ones that, for example, Google has shared, right? But one thing is on the atmosphere, one thing is on the land, right? And the interaction, there's so many, they're so complex, right? From local depressions that we somewhat ignored to bridges and culverts, right? There's so many things that some of the physics-based models can include, and we sometimes ignore because there are too many. But how you can even put that in AI, that's still something that we are not even sure, and I don't think we're gonna be there.
Other questions? Aubrey?
Two, but maybe first one, so what do you evaluate these models with? Because the observations can be pretty challenging. I'm thinking some of these big events, it blew all the stream gauges, so you're not evaluating against stream gauges. So how do you evaluate these different models?
Great question. We got that from the reviewers. We were able to survive them so far, right? And yeah, that obviously, okay, so let's say a couple of things. At least in Puerto Rico, all the stream gauges are somewhat higher in the elevation, right, in the watershed. So they're not on the coastal realm, no. So the 2D portion of that model will not have a stream gauge. They're way higher, right? So we were able to calibrate our 1D models with that. Obviously, in Puerto Rico, we have, 60-something gauges, which is a lot if you compare it with other islands, which don't have nothing. But they're mostly focused on the big rivers. So then there's also limitations. So we went kind of like this regionalized calibration, in which we got 2 or 3 stream gauges and watersheds, use that, get their average, and then apply to the rest of them. And then comes for the, and then what we do for the 2D, right? There's no high watermarks because they take a lot of money to do it. And the USG is the one that does them, but they don't go a lot to Puerto Rico to do it, right? So Fiona, Maria, Irma, they only have 5 points and they're all on the coast, right, in the ocean. So therefore, we don't have high water marks. The other option that we tried to do was satellite imaging with AR5 and all that. We have seen doing that in other Caribbean islands for other events. Again, in that case, you're only doing the 2D spatial extent, right? Not the vertical, obviously. But funny enough, for all the 3 storms, there was no data. Like it was either a cloud or it passed by in a different time. And I'm like, yeah, lucky us, right? So, well, lucky, not lucky, because then the reviewer gets angry, right? So we ended up going with a third approach, which is probably what we call the bare minimum, right? Which is the sensitivity analysis, in which we just assess, we tweak our parameter from that model that we are not aware of, like the Mannings, the infiltration parameters. We increase them 10%, decrease it by 10%, and see their influences on the total outputs. Our findings show that I think it was the hydraulic conductivity was somewhat significant, but the most was the Mannings roughness, obviously. But their changes was really minor in terms of flood peaks and so on. So if we got our parameters wrong, the major outcome will not even change at all. So that's probably what how we call this, kill the reviewer, and now at least it's under, not more under the gun. But also the other options could be, a Monte Carlo approach. But in this case, right, each simulation costs, 4 hours, right? It's gonna add up quickly, so we only didn't went that way. But yeah, it's a challenge. For the Caribbean, it will also be a challenge. So, for example, that work in the Caribbean with the coastal flooding, what we can do, well, we can compare my approach of simplifying the mesh, right, all that, for Puerto Rico with a model for Puerto Rico that was made high resolution by the Army Corps. If they two pair well enough, means that my methodology is good enough, then I can do that for the other islands and I'm somewhat safe. And that's kind of like the goal with that one. Because again, there's gonna be less data there, right? So.
Any final quick questions?
One quick question, like you ran the model for like 1.8 million nodes for the ADCIRC. I'm curious, what's the model runtime for those cases?
Yeah, so let's see. We're probably running in. We play with the amount of cores, right, and the time that we have to do. To give you an example, that 1.8 million node, it could take, let's see, on 380 something cores, right, computer cores, it could take probably 6 hours or so. Again, if you want to make it shorter, then you put more cores and vice versa, right? We tend to go in the way of, let me make it slower, let's just use less cores, right? But then I launch more at the same time. So then I make small batches of, I don't know, 20 or 50, and they just go in loop, and then I can send 5 of those versus trying to make it faster each simulation. So that tends to work better with our configuration.
All right, let's thank Felix again.